Shivani Ghatak. I'm a lecturer at the School of Environmental Sustainability. I'm excited to be the moderator of this morning panel on global perspective on climate and water. I would also like to welcome our panelists and truly appreciate their time. So, our first speaker today in the morning, Dr. Matt Roddle. Dr. Roddle truly wanted to be here physically and wanted to join us here at the campus. But due to recent executive order, his travel request has been denied. But we are very delighted to have him over Zoom, and we're really thankful. Dr. Roddle is the Deputy Director of Earth Sciences for Hydrosphere, Biosphere, and Geophysics at NASA Goddard Space Flight Center. HBG comprises more than 400 scientists and engineers within 5 laboratories involved in remote sensing and numerical modeling of land and ocean processes and related applications. He is also a member of the science team for NASA's GRACE mission, and he'll be talking about that today. He also leads Global Land Data Assimilation System and projects focused on monitoring groundwater storage changes, mapping, and forecasting drought and wetness. He received many awards. I'll be just mentioning few of them. He received a Presidential Early Career Award for Scientists and Engineers in 2006, a NASA GSFC Earth Science Achievement Award in 2007, Robert H. Goddard Award for Exceptional Achievement in Science in 2011, and Arthur S. Fleming Award for Outstanding Federal Service in the area of basic science in 2015. He was also elected to the rank of AG Fellow in 2022, and he has more than 150 peer-reviewed publications, and he appears as Clarified Web of Sciences as highly cited researcher. Please welcome Dr. Matt Roddle.
So yeah, I'm Matt Rodell. I'm from NASA Goddard Space Flight Center in Greenbelt, Maryland. If you're not aware, studying the Earth from space is part of NASA's charter. Some people are surprised to hear that. They think about planets and deep space and all that. But yeah, we study Earth from space, which gives us a unique vantage point for studying the Earth. Today I'm going to be talking about global perspectives on climate and water. So I'll give you an overview of the global water cycle and how it's being affected by climate change and direct human impacts. So the global water cycle, as you probably know, is the movement of water around the Earth. So it starts with water evaporating from the ocean. Some of that water moves over the land and falls as snow and rain. That snow and rain, some of it is going to evaporate back to the atmosphere. Some of it enters lakes and rivers and flows back to the ocean, and some of it penetrates the soil and becomes soil moisture and deeper groundwater. And eventually this water continues to cycle. And this is what gives us fresh water on land, which is, of course, critical to life on land. The numbers here are based on the latest water storage estimates and flux estimates from a combination of ground-based observations and satellite observations. And these are, the units here are 1,000 cubic kilometer per year. So to give you an idea of what that is, the Great Lakes hold about 23,000 cubic kilometers of water. So if you look at the cycle here, for example, the amount of water flowing out of all the rivers around the world into the ocean is about double the capacity of the Great Lakes per year. So these are huge, huge volumes of water. And one of the things I want you to take away from this is to think about, when you think about climate change, it's not just the atmosphere warming and it feels a little warmer outside. Some of the most significant impacts and the most consequential impacts will be changes to the water cycle. So of course, the water cycle is a lot more complicated than that last figure. This is one of the most recent schematics from USGS. And so you can see there's a lot going on with the water cycle. And some of the things are direct human intervention. So things like, when we grow crops and we irrigate those crops, we're pumping water out of out of the ground and using water from streams and rivers and reservoirs, and a lot of that water evaporates into the atmosphere and doesn't continue to flow downstream, or it can deplete the aquifers. So we actually have direct human impacts in the water cycle, and it's a very complex system. So speaking of groundwater, when we talk about the amount of water on Earth and where it is and what people use it for, 97.5% of the water is in the ocean. That's not very surprising. So only 2.5% of the water on Earth is fresh water. Of that, about 2/3 is locked up in glaciers and ice sheets. So then when we take that fresh water and look at how it's divided up, when you talk about the surface and the atmosphere, the water that you can really see on land and in lakes and rivers, that's actually only a small, less than 1% of the total fresh water. So these are, it's much less than the total amount of water on Earth. In terms of how the water is used, there on the right side here, there are two sort of freshwater use schematics. The top is the total freshwater use, and it includes things like use for industry and power consumption or power generation, where if there's a power plant located along a river, it might use that water for cooling and then dump warmer water back into the river downstream. So the water is not actually lost. Consumptive water use, shown in the lower right, is things like agriculture, where water might be pumped out of the ground or taken from a reservoir, spread over the crops, and a lot of that water then evaporates and is actually lost from the area. So we call that consumptive water use, and we estimate that anywhere between 80 and 90% of the consumptive water use is for agriculture. So growing the food that we eat and the textiles and that sort of thing uses a lot of fresh water. It's a lot more than just what you use for flushing your toilet and brushing your teeth. When you think about saving water, you can also think about how can I reduce my total water footprint, including the food I eat, that sort of thing. So the Intergovernmental Panel on Climate Change, or IPCC, is the worldwide body of scientists that basically comes up with reports every few years on the current state of the climate around the world, and then provides projections of how the climate's going to change in the future, given the reality of global warming. So these are 4 maps of different possible futures. Basically, what would the world be like at the end of the 21st century with these different levels of global warming. The top left panel shows 1.5 degrees Celsius global warming. Well, guess what? We're already there. If you've been paying attention to the news, we're actually already at 1.5 degrees Celsius above the pre-industrial average. So these are the predictions from the models of how precipitation would change in terms of percent of precipitation. Now, you might look at this and think like, wow, there's a huge change of precipitation over Northern Africa. But remember, these are percentiles, or percentages. So if you only have an area in Northern Africa, in the Sahara Desert that gets 1 or 2 inches of rain per year, a 40 or 50% increase is really not that much rain. You're going from 2 inches of rain to 3 inches of rain, right? So the bigger changes are going to be where there are we already have large amounts of precipitation, and the lines in the hatching are areas where we're less certain about the results. So the models didn't necessarily agree, or that it wasn't a statistically significant change. But as we go to the larger global warming, if you go to the 4 degrees Celsius global warming in the bottom right, then we can see that there are a lot of areas where we are more confident that there are going to be some big changes in the amount of precipitation. But then there are other areas, there are a lot of areas when we just don't know. And so that's one of the reasons we continually have to do this, because we don't have a great understanding of exactly how things are going to change. It's important to continue to monitor and to improve our modeling and to improve our understanding. Now, I mentioned I work at NASA and that we have a unique vantage point from space. So so part of the motivation of what I do is that we just don't have adequate monitoring of all the variables that we would like to monitor based on ground-based measurements. The top left map shows the global telecommunications system meteorological stations. So these measure things like air temperature, precipitation, solar radiation, wind speed, humidity. And you can see that the networks look pretty dense when you look at it from at a global perspective. They're pretty dense over, for example, the eastern United States or Western Europe. But then there are other parts of the world, Central South America or Central Africa, where it might be 60 or 100 miles between each station, and that's really not adequate in order to characterize the weather at any given time. Similarly, for things like groundwater on the right, so the Global Groundwater Monitoring Network are groundwater wells where they have reported data that are collected in the Netherlands, and you can see some areas there's a lot of reporting, other areas nothing. Even in the U.S. in the bottom right there, the USGS collects data in their Global Groundwater Monitoring Network. These are long-term records. They actually have a lot more wells than this, but these are long-term continuous records with pretty frequent observations. And there's good density up in the northeastern U.S. and then the rest of the U.S. There's large. It's a long way between wells that are reporting. The lower left shows river flow stations that are collected by the Global Runoff Data Center. And the cooler the color, the more recent the observations that are available. But some places, if you think about like the Nile River in Egypt, one of the most important rivers in the world, you can't get data on flow through the Nile past 1983. They just don't share those data. So this is why it's important to monitor the Earth from space. We don't have any political boundaries to deal with. We don't have to worry about people sharing data and that sort of thing. This shows the 20 or so active Earth observing satellites that NASA has in orbit. This is just NASA satellites. There are also European satellites and NOAA satellites orbiting the Earth that add to this constellation. But these are the NASA satellites making all sorts of different measurements of the Earth, not just water, but other things like the health of the vegetation, fires, atmospheric variables, cloud cover, rainfall. And we can incorporate these into our models. So we don't have perfect coverage even with the satellite observations, but we can integrate them into our numerical modeling systems that then provide predictions and fill in the gaps. So this is from NASA's Global Modeling and Assimilation Office, and shows each dot is an observation that's being assimilated into their model. And it's pretty cool. You can see you can sort of see the satellite tracks, and you can also see lines that represent measurements on aircraft and that sort of thing. So again, better coverage in some parts of the world than others, but we're doing a lot better than we did with just the ground-based observations. So one particular satellite system I want to talk about is GRACE. So most remote sensing systems, when I say a remote sensing system, I mean a satellite that's making measurements of the Earth from space. Most conventional technologies basically look down at the Earth and make a measurement of some wavelength in the electromagnetic spectrum, which is shown in the upper right there. And different wavelengths are useful for different types of measurements. But all of these this type of measurement technology is limited in that you can only measure things in the atmosphere or on the surface or near the surface of the Earth. But if you're interested in something like groundwater, this type of system is not going to work. So NASA came up with a really ingenious technology that they launched in 2002. So the first satellites were called GRACE, and we now have a second pair of satellites called GRACE Follow-On, which launched in 2018. And what these satellites do is, instead of looking down at the Earth, they actually measure each other. They're measuring the orbits of each satellite. So there are two of them. They're orbiting the Earth, one following the other about 100 miles apart. And every 5 seconds, they're making a measurement of that 100 mile distance has the accuracy about the size of a red blood cell. So extremely precise measurements. Why are they doing that? Because the orbits are affected by the gravity of the Earth, and the gravity on Earth is not uniform. If there's a mountain range, that means there's more mass. Gravity is directly proportional to mass. So as these satellites fly over a mountain range, the orbits are actually perturbed by the gravitational potential of that mountain range. But the measurements Grace makes are so accurate that I can actually see changes caused by things like water stored in the land surface. So imagine there's a big snowstorm and you had a foot of snow on the ground. That's actually enough mass that affects the orbits of these satellites. And based on observations over the course of months, we can actually see changes we can estimate changes in the water stored on and in the land surface based on these GRACE satellite observations. And they're not limited to the surface. So as groundwater storage changes, that also changes the mass, and these satellites are able to measure it. It's really unique. It's the only way to do that. So the types of things we can do with that are measuring the amount of water stored on and in the land surface in a given region of interest. So this is showing time series and animation for California's Central Valley watershed. Central Valley is one of the most important agricultural productive regions of the U.S. and the world, and it's been hit by a series of droughts. And when there's drought, you don't only have loss of water caused by the drought itself, but the farmers rely more on the groundwater. They pump a lot of groundwater out of the ground, and so you see this extra loss of water storage caused by reliance on groundwater pumping aquifers. The aquifers don't fully recharge after the drought. They just don't have the opportunity. It takes a long time, and it requires that they're not being pumped at the same time. And so there's a long-term trend in the Central Valley of terrestrial water storage decline, which is mostly depletion of water in these aquifers. So using the GRACE data from 2003 to 2024, if you look at each location on Earth and you estimate the rate of change of terrestrial water storage at that location, this is the map that you get. So blues mean that on average, the water storage has been increasing at that location basically since 2003. And the red areas mean that water storage has been decreasing. Again, the terrestrial water storage is all the water. So that's the groundwater plus soil moisture plus snow, surface water, all the water sort of considered as one quantity. And we look at how that's changing over time based on the GRACE data. And what we see is there are some areas, and these are color coded. So the green mean that it's sort of natural variability. So maybe there was a recent drought, like in southern Brazil, where it's been very dry lately, and that makes it look like over the long term, terrestrial water storage is declining there. But in reality, that might bounce back, and they might have a wet period, and then it'll come back to one of the middle colors, or maybe become blue. And there are other areas like that, like Central Africa has been very wet since about 2018. A series of wet events that we call pluvials. But then there are other parts of the world shown in red where there are direct consequences of climate change, and the most obvious ones are ice sheet loss in Greenland and Antarctica, and glacier loss in areas like the Gulf Coast of Alaska. You'll see if you're curious about the mix of reds and blues in Greenland and Antarctica. I'll just say that the color scale there is limited, so the negative 2.5 centimeters per year is the extent of the color scale. But we could actually extend this out and make it so that the red trends there are actually a lot darker red than the blue trends. So they greatly outweigh where there may be some increase in terrestrial water storage due to increased precipitation. There are also some issues with something called post-glacial rebound, which I won't get into, but basically suffice it to say that the average ice loss from Greenland and Antarctica is huge, and that's about half the contribution to sea level rise is loss of ice sheet thickness. The orange areas are places where there are direct human impacts, and a lot of these are due to groundwater pumping, like I was mentioning. So these are agriculturally productive regions. They pump a lot of water out of the ground. The levels in those aquifers are experiencing a long-term decline, and so we see terrestrial water storage decreases. That if things don't change, if they don't start to reduce their overconsumption of groundwater, eventually that groundwater will either run out, the wells will go dry, or they could become too salty for the water to be used. So just to summarize, the impacts on the water cycle will be the most noticeable consequences of climate change. We use satellite remote sensing because ground-based observational networks do not provide adequate spatial and temporal coverage. We have a fleet of Earth observing satellites. NASA has about 20, and then there are others from other agencies and around the world. I mentioned GRACE and GRACE Follow-On, which are two satellite systems that I've worked on for a long time, and they're unique in their ability to measure things like groundwater storage changes. And what we see in the trends in terrestrial water storage reflect a combined effects of climate change, direct human impacts, and natural variability. So I'll just leave you with this. This is just some resources if you're interested, and happy to take questions.
I would actually like to welcome our next speaker, Dr. Matthew Child. We would also like to draw our attention to our continent now, and more specifically on the transboundary water resources that's shared by the United States and Canada. Our next speaker actually has come from Canada. He is a physical scientist with the International Joint Commission's Great Lakes Regional Office in Ontario. Dr. Child's primary role at IGJC is to support the Science Advisory Board's Science Priority Committee, which advises the Commission and its Water Quality Board on a range of scientific matters. He serves as staff leader for several ongoing Science Advisory Board projects addressing the influence of the changing climate on Great Lakes water quality. Please welcome Dr. Child.
As has already been introduced, I am with the International Joint Commission, and as the name suggests, the International Joint Commission, or IJC, is an international organization and is staffed by both U.S. and Canadian citizens. I'm on the Canadian side of the IJC House. However, I do work side by next daily with U.S. colleagues at IJC, at many federal agencies, and with faculty at universities that have ongoing federally funded projects. And as I get started on my remarks, I just wanted to acknowledge the uncertain times that we find ourselves in and the importance of continued cooperation and dialogue to address our transboundary water resource. So for those of you who aren't familiar with the IJC, really quick reminder, we were formed over 115 years ago through the Boundary Waters Treaty between the US and Canada. The treaty establishes two primary roles for IJC. The Commission fills a quasi-regulatory role whereby we issue orders of approval for dams and other structures that affect transboundary water levels and flows, and we investigate issues and offer recommendations on topics that the federal governments refer to us. Then, in the 1970s, the US-Canada Great Lakes Water Quality Agreement assigned an additional role to the IJC to provide regular and ongoing advice on Great Lakes water quality issues. These are the transboundary watersheds between the US and Canada. Overall, there's some 300 individual watercourses, tributaries to the basins that drain to major rivers in each of these watersheds that span our international boundary that covers some 4,500 miles of running length. So they're sort of shifting to some remarks about climate. There is little doubt, as we heard yesterday from Dr. Glick and from Matt a moment ago, there is little doubt that changing climate is affecting and will continue to affect certainly the planet as well as the US-Canada transboundary waters. This slide shows modeled changes to average annual temperature for warming levels of 2.7 and 3.6 degrees Fahrenheit relative to the pre-industrial period of 1851 to 1900. Data from recent years confirm, as Matt has already indicated, that we are experiencing increases of in excess of 1.5 degrees Fahrenheit. And you can see for both scenarios that the northern areas of the US at its boundary with Canada are projected to warm by at least 4 or 5 degrees Fahrenheit, which is more than the global average. And you'll also note that for both scenarios, warming is expected to be greater along the eastern portion of the transboundary. This slide shows projected changes in average annual precipitation. And of course, I'd ask you to focus on the northern portion of these projections. And precipitation is expressed as a percent change relative to that pre-industrial period. Under both scenarios, precipitation is projected to increase, especially in the eastern portion of the transboundary. Precipitation changes are projected, as you might expect, to be larger at higher levels of warming. And so these slides show us not only will changing climate affect the transboundary, but it will affect different parts of the transboundary differently. And so since we're here in Chicago, and since my work is very much focused on the Great Lakes, I thought I might illustrate some of the implications, drivers and implications of changing climate at a more regional scale, particularly the Great Lakes. There is a panel following this one on the Great Lakes. We've been working with the conference organizers to ensure that there's not overlap between these remarks. So this slide orients us to the geography and its downstream receiving environment, the St. Lawrence River. The lakes, as you know, are the largest freshwater body on Earth. 8 U.S. states, 2 provinces. It's a really big geography. To understand the effect of changing climate on lake levels, which I'd like to offer a remark on now, we need to understand observed lake levels since record keeping began roughly 160 years ago. And to keep things manageable, let's use Lake Michigan and Huron levels as an example, although they are separate lakes. As you know, they are connected by a wide connecting waters, the straits at Mackinac, and thus function hydraulically as one larger system. And the top panel shows water levels over the past 10 years, with observed water levels shown as the blue points, long-term average levels shown as the orange line, and one-year averages shown as the blue line. The point here is that levels fluctuate within each year in a pretty predictable fashion, a pretty predictable and recurring pattern, with highest levels in the late spring and early summer in response to snowmelt and spring storms, and lowest levels in midwinter. Typically, levels fluctuate within each year by about 0.5 meter or 1.5 feet between the summer high and the winter lows. I'm going to try to find my mouse. I don't see it. That's okay. I learned a long time ago to bring paper notes as well. Over longer time scales, various planetary scale forces also influence water level changes. Matt touched on a number of those, as did Dr. Glick last night. And those changes are much more pronounced than the intra-annual changes that we observe annually. The bottom panel shows Lake Michigan Huron water levels, where average annual levels are the black line, and the long-term average is the red line. Note that levels fluctuate by roughly 6 feet between the lowest lows and the highest highs over a multi-decadal time scale. Although Lake Ontario is a bit of a special case, and we can talk about that later if you wish, this pattern is generally representative of the other lakes, of Superior and Erie as well. So two key points I want to make relative to lake levels. First, the primary driver of lake levels across the Great Lakes is net basin supplies, specifically overlake precipitation, evaporation from the lake surfaces, as well as runoff from the surrounding watersheds. The overwhelming determinant of lake levels is nature. Although there is a diversion into the Great Lakes Basin and Lake Superior at Long Lac and Agokie, and a diversion out of Lake Michigan right here in Chicago at the Sanitary and Ship Canal, as well as dams on the St. Mary's River at Sault Ste. Marie and the St. Lawrence River at Messina, New York. Due to the size of the lakes in their watershed, the maximum influence of those diversions and structures on water levels amounts to no more than several inches on a system that fluctuates by up to 6 feet. The second point I want to make is that although different climate models don't all agree on how lake levels will change in the coming decades under varying warming scenarios, many of the more recent models suggest lake levels may not be too significantly affected by changing climate due to that balance of precipitation and evaporation, although there may be an uptick in lake levels. Most of the models do agree that there will be greater variability, and we're going to have to get used to lower lows and higher highs that perhaps occur more frequently in the future than they have in the past. And this, of course, has many implications, especially for our coastlines, where millions of residents live, where there's high-value habitats and ecosystem services, and where transportation, energy, and other infrastructure is very common. In terms of the impacts of changing climate on the Great Lakes, there are several drivers that are important to consider. And this slide shows expected changes in precipitation for 2 warming scenarios that use the acronym RCP, or Representative Concentration Pathway. And this is IPCC nomenclature. Matt referred to the International Panel on Climate Change. RCP 4.5 is a moderate scenario in which emissions peak around 2040 and then decline over the balance of the century, whereas RCP 8.5 is a worse scenario where emissions continue to rise throughout the 21st century. And for both emissions scenarios and for the 2 20-year time periods shown, as compared to the baseline period of the early part of this century, model results, as you can see, show increased precipitation pretty uniformly over the Great Lakes Basin, with the southern and western parts of the basin experiencing the most significant precipitation increases. And other studies have shown that precipitation increases will be greatest during the spring and early summer. This slide shows lake surface temperature changes for each of the Great Lakes under the moderate emissions and high emissions scenarios. Lake surface temperatures, or LST, as shown in the slide here, are expected to increase for all lakes under both scenarios. As you might expect, changes are greater for the higher emissions scenario. The northern parts of the basin, particularly Lake Superior, will warm more than the southern parts. And as you can see, for all lakes except Erie, strong warming is projected in spring and early summer, which is likely to result in earlier and more intense lake stratification, which does have significant ecological implications for the lakes. This slide shows declines in the number of days in a year that ice is present on the lakes for both emissions scenarios and for 2 different 20-year time periods. Note that all lakes are projected to experience significant declines in ice duration. In addition, other studies of conditions over the past 20 years, as well as modeling projections that look into the future, show that on average, freeze dates are occurring later, maximum ice cover is diminishing, ice breakup dates are occurring earlier, and interannual variability is increasing. So how are these observed and predicted changes, how will these observed and predicted changes affect the Great Lakes and therefore influence management policy, investment, and other decisions and priorities? On this slide, I attempt to summarize some of the implications across 3 categories. And although most of these impacts are negative, at least in my opinion, there are some positives. And I'll touch on a couple from each category, and then we can elaborate on others during our discussion and over lunch if you wish. So some of the ecological impacts are perhaps best understood. And they include, for example, impacts on native fish communities in the Great Lakes. And it's expected that for species that are considered desirable by sport, commercial, and tribal fishers, those gills tend to be cold or cool water species, and therefore they will be disadvantaged, competitively disadvantaged as the lakes warm. Further, many desirable fish species like lake trout, salmon, and whitefish, to name a few, are fall spawners, and the loss of ice cover will expose those spawning habitats to increased wave action and other disturbances during the winter months that may limit hatching success. We can also expect impacts to human health and safety. More intense storms and wilder weather will result in flooding of tributary floodplains and coastal areas. We're seeing that increasingly. In addition to affecting personal property, critical infrastructure related to the safety and security of all of our communities are at risk. Many sewage treatment plants, many water purification plants, a great deal of our transportation and energy infrastructure are located in coastal areas. The loss of shorefast ice will expose our coasts to increased winter wave energy, which will result in increased coastal erosion that affects the same infrastructure. And then finally, there's a number of socioeconomic and cultural impacts shown here. All of these lists could be longer, and you probably already identified some things that you might include. The socioeconomic and cultural impacts are perhaps the least well studied, and that's beginning to change, and that's heartening to see. Less ice cover is good for Great Lakes shipping. You can move goods for more of the year, and although there's still costs to maintaining an ice-breaking fleet, there are some operational savings due to reduced ice-breaking needs. There's a loss of winter sports like skiing and snowshoeing, and winter activities like snowmobiling and ice fishing with their associated economic implications. And finally, there's a certain loss of cultural identity that many people feel. What do snow days or winter tires or pond hockey mean to all of you? So what can we do about it? There's strong scientific evidence that changing climate will impact the Great Lakes in many ways. There's a lot of impacts we don't even know about yet. So that's the really negative and bummer kind of part of the talk. And I'm going to try to turn, in my concluding couple slides here, perhaps some more optimistic remarks. And that's because folks here in the Great Lakes have already done a lot of the hard work needed to help us through the changes that are already happening, and that applies to the entire transboundary. In addition to acknowledging the importance of mitigation through emissions reductions, it's also important to acknowledge the significant momentum that exists toward adaptation and resiliency. While there is still more work to be done to align and coordinate ongoing efforts at the federal, state, and provincial, regional, local levels, et cetera, there's a lot of adaptation work underway, and I certainly look forward to hearing more about that over the next panels. My final slide here, I'm almost there. I also think it's important to acknowledge the management and governance arrangements that we have here in the Great Lakes, and this is more important than ever. For over 50 years, the US and Canada have cooperated closely on restoring and protecting Great Lakes water quality through commitments they made in the Great Lakes Water Quality Agreement. It is not an exaggeration to say that the Great Lakes have one of the most highly evolved, arguably the most highly evolved multinational water resource management framework anywhere on Earth. And by way of example, the agreement is delivered through a Great Lakes executive committee that includes membership from federal, state, provincial, regional agencies, tribes and First Nations, among others. There are 10 annex teams set up to deliver results related to 10 different threats and resource values, including one dedicated to addressing climate change impacts. The Great Lakes have long enjoyed strong bipartisan congressional support, and hopefully that will continue. The U.S. Great Lakes Restoration Initiative has seen a generational scale level of investment in the Great Lakes for well over 10 years now. And for many of the priorities the GLRI has tackled, the end is in sight, and it is important that resources be available to finish the job. The agreement and related federal programs have helped bring Indigenous science and tribal perspectives into decision-making, and has led to the formation of literally hundreds of partnerships at the local and regional levels. And I could go on, but in the interest of time, I'll conclude my remarks there. Thank you.
Our next panelist, Eliza Swedenborg, once wrote, "Water is increasingly being recognized as a climate change priority, but climate change mitigation and adaptation efforts are far off track." Eliza Swedenborg is strategist, writer, researcher at World Resources Institute, and she is mother of two. Eliza will add a different perspective to our ongoing discussion today as she sees water as a vital element of our interconnected global challenges and an essential lens through which to envision change. In her work, she seeks to understand where we are most out of sync with water, intersecting with climate, agriculture, cities, nature, and well being, and how shifts in economics, trade, and finance might bring us back into balance with water and each other. Please welcome Eliza Swedenborg.
So I'm going to start with a poem. This is Water by Wendell Berry. I was born in a drought year. That summer, my mother waited in the house, enclosed in the sun and the dry, ceaseless wind, for the men to come back in the evenings, bringing water from a distant spring. Veins of leaves ran dry, roots shrank, and all my life I have dreaded the return of that year, sure that it is still somewhere like a dead enemy's soul. Fear of dust in my mouth is always with me, and I am the faithful husband of the rain. I love the water of wells and springs and the taste of roofs in the water of cisterns. I am a dry man whose thirst is praise of clouds and whose mind is something of a cup. My sweetness is to wake in the night after days of dry heat, hearing the rain. There was a World Bank report that came out a few years ago, and they had a chapter on rainfall as destiny. Drawing from research from communities across sub-Saharan Africa, they found that if a child is born and experiences a dry shock, droughts in the first 1,000 days of their life, they're likely to suffer from that their entire life. More likely to be malnourished, to experience stunting, not to grow as tall as their peers, not to attend as much school, not to earn as much money. When we think about drought, one of the primary ways in which we're experiencing climate change, we tend to think of it as an event that ends as soon as the next rain begins. But clearly its impact is much more profound. I find that when we tend to think about climate as a carbon story. But if we look at the story of climate through the lens of water, through H2O instead of CO2, we find a different story, one that in some ways is more connected to the human experience, and one that also offers different paths forward. So my co-panelists, Matt and Matthew, did an incredible job. I'm not a hydroclimatologist, so I'm not going to try to pretend to be one. Talking about especially the impact that GHG emissions, accumulating in the atmosphere, increasing temperatures, distorting the water cycle at a global level, how that impacts us. And I'm going to talk about another driver of climate change, which I think is much less acknowledged, although emerging science, really cool science, like emerging science is telling us how important it is. And that is the role that nature plays in regulating the climate. How the ecological organs of our planet, not just through carbon, but through temperature regulation, through the water cycle, are also playing a critical role. To start, I would like you to close your eyes, invite you to close your eyes. You don't have to close your eyes, but invite you to close your eyes and imagine it is a hot, muggy summer day, and you're a little sweaty. You might be a little sunburnt. Wear your sunscreen. And the sun is going down, and there's a cool wind coming in, and the rain starts. And I'd like you to imagine, where does your rain come from? And you can open your eyes again. Yes, from the clouds, yes, from the sky, but the rain also comes from upwind. And some of the time that means it evaporates from the oceans, and then it travels through the atmosphere, condenses, and falls to us. But about half of the time, just under half the time, that rain comes from the land, which means land plays a really critical role in regulating our climate. Such an important role that some colleagues of mine at the World Resources Institute released a report a few years ago called Not Just Carbon. Not just carbon, capturing all the benefits of forests for stabilizing the climate from local to global scales. And as I said, a lot of this happens through the water cycle. So my version of it is much more simplistic than we saw from my colleagues, oversimplistic. But I want to focus on specifically on the cloud, that little icon that I added to the side, the cloud and the rain, and understanding that condensation, which forms precipitation, is a function of heat and of water vapor saturation. So if the air is hotter, you need more moisture in the air in order for condensation to form precipitation. And vegetation plays a really big role here. It's not just the global temperature rise. Vegetation also plays a big role. We all can imagine, standing under an incredible, incredible forest. The forest also, or the land, will cool the air, and when they transpire, they release water into the atmosphere. So they play a really important role also, not just on the land, but in regulating our precipitation. This is another version of the water cycle from the Global Commission on the Economics of Water, which focuses on this green water story. So you see blue water on the right here. Blue water is the water in our rivers, in our lakes, in our groundwater, and green water is the water in soil that plants have access to and transpire into the air, which then can, through what's called terrestrial moisture recycling, circulate back in precipitation on land. And a lot of that happens locally, and just really cool, another really cool piece of research from the Global Commission on the Economics of Water, it also connects us over very long distances, where some of that moisture that is either evaporates or transpires can travel across a continent to form rain far away. So the first message, again, is land and nature play a critical role in climate regulation, much of which happens through the water cycle. And the second message is that when land is deforested or degraded, the precipitation locally and downwind becomes more erratic. This is a map from Global Forest Watch. It's one of the data platforms that we have at the World Resources Institute, thanks in part from data from Matt's colleagues at NASA. And this map shows forest loss over the last 20 years. Pink is forest loss. There's kind of a mauve, kind of purple color that's forest loss due to fires. Green is tree cover, and then blue is tree cover gain. And this just over the last 20 some years, we've lost about 12% of the world's tree cover. That's 12% of these critical ecological organs, which are also playing a role in stabilizing our climate. And a lot of that deforestation is happening in places like the Amazon, the Congo River Basin, the Mekong, and Indonesia, these rainforests which play an outsized role as sort of engines of the water cycle within their region. So even if we manage to abate carbon back to pre-industrial levels, if our ecological crisis continues, we'll still experience this climate derangement. My third message is we can do something about it. We can protect and restore nature's regulation of precipitation, of climate. And we have evidence of this. These are images from the Loess Plateau in China. They're one of the biggest regreening efforts that I'm aware of in the world. And one of the concerns that people sometimes have about planting trees is, well, trees are thirsty. They'll drink a lot of water, they'll take it from the ground, they'll transpire it, and then there will be less water for people who live downstream, for example. But research on this regreening effort showed that even though transpiration increased, the greenery was pulling more water from the ground, precipitation was also increasing. So they were, through that sort of cooling and humidification that was happening, more rain was falling, and it was staying within the system. So when we look at these three messages together, I think on some level, it's incredibly intuitive. Like, of course, Of course, forests and wetlands and the land plays a role in our climate. Of course it does. But it's not as clearly in any of our global agendas. In our agenda on climate action, through the Paris Agreement, in the Global Convention on Biodiversity, on our nature agenda. It's not as clearly a part of the water agenda because we tend to focus more on blue water as opposed to green water. And I think that's a huge mistake. And for me, it's really important that we tell this water climate story and not just the carbon climate story, which is also very real and important, but because I think that there's two shifts that come of it from it, and on a strategic level, in the sense of what should we be doing to address climate change. And one of those is the shift from global to local. So if you change to a more efficient light bulb, that will help to reduce emissions at a global level. If you plant a tree that can, in the right place, that can help to reduce emissions at the global level. But trees are not just carbon sticks. They also play these other really important roles. If you plant a tree, or you plant the right tree in the right place and in the right scale, you're also planting rain, or you're planting your neighbor's rain. And oh, by the way, you're also helping to abate carbon. So that just feels like a really incredible shift in terms of where is their political will? Where does it benefit me to act, my community, acting locally, and in the face of this global commons challenge? And the other shift is more about how we see ourselves, the human role in addressing climate change, where right now a lot of our language is about fighting climate change. We're warriors, we need to sacrifice. And I think that there's a shift when we look at this connection to nature's protection and restoration, to restoring the water cycle, that is more about being a caretaker. How can we take care of our planet? How can we help to restore nature's natural abundance? And I'm going to go down a really quick rabbit hole. Do I have time for a quick rabbit hole? Okay. A little linguistic rabbit hole. So the word regulate, I use the word regulate a lot. Nature regulating climate through the water cycle. This word, I think we think of like policy, like government regulations a lot when this word comes up. It first shows up in the 15th century from the Latin word for rules, and it means to control by rules. Another word, dysregulated, comes up. It first appears in the late 50s, and it shows up in medical texts for neurology and psychiatry. And this is dysregulation is when you have the impairment of your physical, like a metabolic, physical, psychological processes. So in therapy speak, if any of you are fluent in therapy speak, if you say you're dysregulated, it means there's just too much happening in my life. I'm overwhelmed, I'm overstimulated, and I can't manage these emotions that I'm having. Co-regulation is widely used on parenting Instagram and parents in general for a certain generation. And it's when two people help each other to regulate their emotions. When a baby is born, that child does not have the ability to regulate its own emotions. So its caretakers, its mom, its dad, its caretakers need to help the child to regulate, to find a place of calm. But it's not just limited to mothers or parents and children, but that's where it's widely used. And what I think is really interesting about this journey is that we go from a place of control to a place of care in how we understand the word regulate. Okay, I have one more water cycle picture. This is art by one of my favorite artists. Her name is Christy Belcourt. She's an indigenous Métis artist who's based, I believe, in Alberta. And this is one of her prints. And in one sense, this is telling the story of a Thunderbird woman. I do not feel qualified to tell that story. But in another sense, this is another version of the water cycle, where you see this woman who is intimately connected to the natural world, intimately connected to the rain. They're all connected to each other. These, again, us as part of the living system that's regulating the water cycle. So finally, I'm going to get to Laudato Si. I am not Catholic, and I will admit I did not read the encyclical until recently, and I was really struck by it. I was struck by the lessons from St. Francis. St. Francis reminds us that our common home is like a sister with whom we share our life and a beautiful mother who opens her arms to embrace us. If we feel intimately united with all that exists, then sobriety and care will well up spontaneously. And throughout the encyclical, he talks about the shift from control to care. And why I think that matters is we need climate warriors. Absolutely, we need climate warriors. Climate is an incredible global injustice. And some of us are called to be caretakers. So I hope that if you feel called to being a climate caretaker, to being a faithful caretaker of the rain, of the living climate, that you will heed that call as well. Thank you.
We will open the floor for questions, but before that, I'm going to ask, few questions just to when you're gathering your questions. I'm going to take this opportunity to ask questions. So I'm going to start with Matt. Matt, my question for you is NASA planning a future GRACE mission for after GRACE FO, when the GRACE FO ends?
Yeah, in fact, I've been working on the science team developing that mission right now. We anticipate that GRACE follow-on will continue to operate until maybe 2029, 2030. But after that time, we'll need another mission, and we're working on that, and we hope it's going to launch around the 2029 timeframe. Thanks for the question.
Thank you. Question for Matthew. How is changing climate expected to impact nuisance and harmful algal bloom in the Great Lakes? And what can be done to address it?
Yeah, thanks, Deb Jenny. And I think Dan Egan is talking next in the next panel, and he may have something to say about this as well. But the nutrients in the Great Lakes and indeed across the transboundary is a very vexing, very challenging problem. It's not just a Great Lakes problem. Lake Winnipeg, which has parts of its drainage in North Dakota and Minnesota, experiences harmful and nuisance algal blooms. Further east, Missisquoi Bay and the Lake Champlain system, Vermont, experiences harmful algal bloom challenges. Here in the Great Lakes Basin, some of the shallow embayments, Saginaw Bay, Green Bay, just up the coast here. Perhaps ground zero is the west basin of Lake Erie. We all know about Toledo. We all know about the history of nutrient enrichment or eutrophication of Lake Erie, memorialized in Dr. Seuss's The Lorax, among other things. So I'll answer the question about climate in a sec, but I just want to sort of observe that we were successful in addressing nutrient challenges in the Great Lakes Basin once before. It was the proliferation of algae in the 60s and 70s that in large part motivated the governments to sign the Great Lakes Water Quality Agreement and to invest massively in addressing point sources of nutrients to the lakes. Nutrients coming from the ends of pipes, namely sewage treatment plants. Lots of money spent on, in today's dollars, it would be into the billions, I have no doubt. Lots of money spent on expanding and upgrading sewage treatment plants, addressing through regulatory mechanisms, phosphorus content in detergents, and it worked. The lakes recovered. Doesn't mean that there weren't issues through the 80s and 90s with persistent toxics and things, but the nutrient issue was addressed. The governments eased off their monitoring programs a little bit, and before we knew it, the nutrient problem was back. And this time, it's a non-point source issue. It's diffuse sources of nutrients coming primarily from agricultural landscapes. Urban landscapes play a part for sure, but agricultural landscapes are quite demonstrably the driver. And so there's been commitments made to reduce nutrient loads to Lake Erie and other systems. Some of those targets are quite ambitious, appropriately ambitious, but nonetheless ambitious, and they're proving very difficult to address. Unfortunately, climate is going to make it more challenging. We've heard in the talks about increased precipitation and warming water. Increased precipitation and the more intense storms that we can expect in the future will increase erosion from agricultural landscapes where phosphorus and nitrogen and other soil and so forth will be exported to the lakes. Warmer lake temperatures are more favorable to algal growth. The absence of ice in the winters does mean that surface agitation through wave and wind keeps soil particles to which nutrients are sorbed, suspended in the water column, so they're present in the upper water column when things warm up in the spring. So a lot of work being done on both sides of the border to address the nutrient threat, but unfortunately it is going to make it more challenging in light of changing climate.
Question for Eliza. My question is really long though. So you have written previously about the inequity of water and how global drivers are causing local water scarcity. So can you expand on that and share how it connects to the climate story through a water lens? And there is a second part of the question. So there is like when, because of the urbanization and, there is a lot of water scarcity happen, there's a inefficiency of local government sometimes plays a role in managing the water security. So how do you partition between what's a dominant force? Maybe you have seen that, the role of local government in managing the water security versus the impact of climate change on local water crisis. Do you have any thought on that which one is more dominant force in some of your case studies?
So within the water community, people will often say water is local, which is very true. Water is so context specific to locally where you live. And as we've seen through climate change, through ecological crisis, also through sort of economic systems of extraction and exploitation, water is also impacted by these global drivers. But in terms of what's the dominant force, I don't think I'm equipped exactly to answer that question. They're both really important. Water is often quite underfunded at the local level as well. So we need to be acting on climate at a global level. We need to be looking at the sort of economic drivers of over extraction and exploitation, of forest degradation, and we need to be investing in local land and water managers.
Internationally, I think you've said that 90% of water use is due to agriculture. What is the rate in the United States, and how is that used, and also how is it? How does it pertain to the Great Lakes as well? So, United States, what is the United States rate, and what is the Great Lakes? How is the Great Lakes impacted by agriculture? Thank you.
I can try to answer the first part. I think it's, I think for the U.S., I don't know the exact number, but I think it's on the same order. I think the 90% might be at the high end of estimate. So it's somewhere between 70 and 90% globally, and it's probably, somewhere between 70 and 80%, I think, in the U.S. in terms of agricultural water consumption. We tend to be big users of water for other things. Our household use, that sort of thing, that maybe it's less so in the rest of the world. But of course, there is a lot of agricultural water use in the U.S. as well. Regarding in the Great Lakes area, that's I don't know if Matthew can answer that one.
Yeah, I can certainly offer perspective. So as you might imagine, in a system as large as the Great Lakes, we all know this through our lived experience, there's only parts of the basin that are particularly well suited for agriculture. We do have in the southern parts of the basin some of the best agricultural land on the planet. We've got a very hospitable climate to growing crops of different types, and that's part of the complexity of a response, is that the different sectors have different impacts. So livestock producers have a different set of challenges and impacts than the grains and oilseeds, than do the fruits and specialty crops, than do the greenhouses, and so it goes. But generally, a couple of observations. One is that there is the issue of water use, and that is regionally can be very significant. For example, one area I would point to is central parts of the lower peninsula of Michigan. There's quite a bit of groundwater withdrawal for irrigation. So regionally, there can be water quantity issues because of our abundant surface waters. I'm not sure it applies as much to the lakes, but certainly tributaries to the lakes do, through permitting processes, but nonetheless do experience some significant diversions for agricultural use. In terms of water quality, one of the big ones we've touched on, and I remarked on it just a moment ago, would be nutrient impacts. Another one is land cover. We've heard from all speakers the importance of land cover in climate systems and regional and local precipitation, et cetera. I personally think there's lots of cause for optimism relative to the agricultural sector. There's, in the course of my career, I spent parts of the early part of my career trying to make the point with agricultural producers that there was a problem with agriculture, and they weren't buying it. And I think we're past that. I think, producers, they understand that there's a responsibility. They may not shout it from the rooftops. A lot of the producer organizations are on side, and there's been a really big infusion of technical and financial assistance provided to producers to implement beneficial management practices and other activities. So we got a ways to go, but it's certainly a really important sector in terms of quantity and maybe especially quality impacts.
There's also, so we talked about blue water and green water in my comments. There's also something called virtual water. Have all of you heard of virtual water? No? Okay. Peter, thank you. So virtual water is the water that is embedded in products that are traded across the globe internationally. So you might think of sugarcane, for example, consuming a lot of water, and then that sugarcane travels. And so if we think about specifically the US or specifically our region, Peter, I think I've read your book. I think in your book you talk about how, in Peter's book he talks about how in some ways we have decoupled, or we are decoupling water use or water demand from economic growth. But if we are doing that by exporting our water consumption to another part of the world where other communities we're relying on that water or their ecosystems, where we need to look really closely at that in our trade and economic policies as well.
And the 4.5 and the 8.5 trajectories, I'm wondering, which one of those models are we trending more towards, and to what extent do we rely on policymakers and corporations to take action outside of the scientific community?
Yeah, it's a great question, and it's not one I can answer very well. I'm just not really current with where we are with atmospheric emissions beyond what I pick up along the way. But suffice it to say, they're sufficient that we've. I think the most recent data suggests that the global average air temperatures are roughly 1.8 degrees Fahrenheit warmer than they were compared to pre-industrial. So it's getting significant. One of the things that I know that the Commission gets asked a lot about relative to climate is, there's the mitigation side, there's reducing atmospheric greenhouse gases, and there's the adaptation side. And Dr. Glick talked about this yesterday. And for the most part, those atmospheric emissions are, there's procedures to address those, and it's often through international treaty and global commitments. And different countries have taken different positions, including very recently. And those are some things we should be paying attention to and concerning ourselves with. What we are more able to address in the immediate term, and which is being addressed, is the adaptation side. And so it's sort of that dual prong. I'm not sure if that's helpful, but those would be some perspectives on that.
So if I can chime in. Yeah, so I think we're trending towards the high end, and I based on the fact that if you look at the 2024 global mean temperature average, it was 1.5 degrees Celsius above above the baseline. 1.5 degrees Celsius is was a 3.2 or so Fahrenheit. We're already quite a bit above where we want to be. We're already at that low end scenario for the end of the century. And so I think, things don't change. We're heading towards the high end. As to how to respond to that, it's really going to be up to a combination of government, regulations probably, and people and decisions being made by corporations, and potentially changes to different sources of energy. If the was it the National Ignition Facility, if they have a breakthrough in terms of fusion, maybe things will change rapidly in a good way. But hard to know.
This week, of course, we're probably all very scared to see the EPA roll back so many huge pieces of legislation towards a greater push towards deregulation, which is terrifying for things like water. And I was just curious what your all perspectives are on how things like this agreement between the US and Canada, when we're having so much tension with Canada, what does that look like from the Canadian side when the EPA is rolling back legislation protecting our waterways for places like the Great Lakes? How is Canada responding, for example?
The commission was established in 1909, 116 years ago. That's pretty much forever in terms of binational, multinational water agreements. If you look at the ones across the planet, and there's over 300 now, the Boundary Waters Treaty between the U.S. and Canada is almost the oldest. And for me, that's pretty remarkable. That really speaks to a very durable model. That model is predicated on the Commission providing impartial and science-based advice to both governments, to the governments of the U.S. and Canada, on matters that get referred to it. In the Great Lakes, as I alluded to, we have sort of more of a standing opportunity through the agreement to provide advice on any water quality related matters. So to your question about very recent developments that are political in nature, are domestic policy in nature, I'm not able to comment. We must maintain as a commission that perception of unreality of impartial science-based advice. I can tell you personally as a Canadian, there's a lot of interest in the decisions that have been taken, and it's a very, very active point of discussion. You may know that pretty much right now, a new prime minister is being sworn in Canada. That will, I have no doubt, adjust the dynamic. And so we'll wait and see. But it is disappointing to me personally, the developments that we've seen relative to the water resource. And I think probably all of us are here because we care about that resource, and presumably that perspective is shared. Thanks.
I have a question for Matt. We were talking about the water issues between Canada and US. I wanted to ask, how can AI help both nations, both countries collaborate on water management, and what are the biggest obstacles to adopting such tech-driven solutions?
One of the neat things that the IJC Science Advisory Board is doing right now, it's developing a decadal scale science plan. And this plan is predicated on the notion that the governments have been doing, the IJC can sort of critique as can any entity about existing monitoring and surveillance programs of the federal governments relative to the transboundary water resource. But the programs that exist they're very good. They're amongst the best in the world. However, in the opinion of the board, they are primarily geared to understanding and informing and addressing legacy impacts, the things that have occurred historically, contaminants, nutrients, aquatic invasive species that are already in the system and spread of them once they get here, all that sort of stuff. There's not as much emphasis on looking to the future and having a sufficient understanding of the system so that when stressors and threats emerge down the road that may look different than the ones we've addressed in terms of legacy stressors, we need to be ready for that. So we need to reorient some level of investment through new resources to the future. And so that's the reason I provide that background is because to your question, there is immense potential and a great deal of hope and optimism relative to technology helping us look towards the future and become much more effective at a much lower cost in understanding the system. So monitoring and surveillance is an area where there's immense opportunity for tech, autonomous underwater vehicles, thermistor strings and other instruments that literally sit on the bottom of the lake, transmit data, very, very frequently, wirelessly, and can be utilized in decision-making almost in real time. The other part of the discussion that the board has been having is around data management, and that's perhaps where AI, machine learning, and so forth come in. There is an immense amount of data that exists on the system, and I'm talking about the Great Lakes now, but you could apply it to any major system across the transboundary and any other significant watershed throughout the U.S. There's lots of data. A lot of those data aren't particularly discoverable. They're not you can't access them through on the internet. They're not interoperable. They can't talk to each other. The metadata don't line up. And so there is immense opportunity for AI machine learning to assist with that, and through web crawling, web scraping, all that, bring some opportunity. So there's some optimism there. And one of the big challenges, and maybe the hope for some of you who are pursuing your studies here and elsewhere, is data science is certainly one area where there's a significant need.
Yeah, Eliza, building on your wonderful presentation, how do you see the role of narrative, particularly those shaped by personal and community experiences of water scarcity, influencing policy making to address water inequity? What elements do you believe are essential for crafting effective narratives?
I feel underqualified to answer this question, but I love this question. And I think, I work at a think tank. I sort of sometimes imagine us being brains in a jar. If we only bring our left brain, our analytical brain, to the table, we're missing a lot. We also need imagination. We need radical imagination to see not just all of the harm that is happening, but also to imagine a way forward. And sometimes that takes a little bit of poetry. Sometimes that takes, understanding complexity, sense-making differently. And so I think narrative plays such an important role in understanding who we are and what our role is here and where we can possibly go from here.
I would like to thank one more time Matt, Matthew, and Eliza. This has been a tremendous session.